Hi everyone, my name is Tim Kington and this is Coding is for the Birds. Daisy and I are working on a JVM, and today we're going to take a look at some if statements and try to figure out how to make branching work. Let's add a simple if statement to our program and see what opcodes that's going to use. Iconst and iStore is not surprising. iLoad, iconst, and then we have an if. So if icmple, okay. So here are a bunch of instructions that are going to be comparing integers. The I is for integer, so compare equal, compare not equal, less than, greater than or equal, greater than, and less than or equal. It's getting its arguments from the stack, and the order, so less than, we're going to have to check that. It looks to me like value 2 is on top of the stack and then value 1 is under it, but it'll be really easy to tell if we get that backward. So all of these opcodes are probably going to use the same code. They can pop two things. They're going to do a comparison, and then they're going to decide where to jump. The other thing is this command is going to have 2 bytes after it. And these are the location that we're going to jump to after the comparison. Yeah, so this is a 16-byte value. And then we're going to jump to that location if the condition was true. Okay, so let's start with the A4. I guess this is going to wind up being a range, so we'll probably put it in here. All right, so let's create a type for that. Now here we need to make a decision. Any opcode that jumps is going to have to send information back to the engine about what the next instruction is to execute. So that's why I added this return value as an int originally. If we look at the definition of the opcode, the range of these jumps is only 64,000 opcodes or bytes. So I think that's probably the limit on a jump in the JVM. And if we look at engine, right now engine is just looping through our opcodes and assuming that we're going one by one, right? We increment our program counter every time. We always get the next opcode and execute it. And we're using the return value right now to tell us when the function is complete. When we get a return opcode, we return -1. Presumably we're going to have jumps that can go backward for loops and things like that. So we will need to use -1, some negative values. I guess -1 probably is never used because that would jump back into the middle of the previous instruction. So that's probably impossible. So maybe we can still use that. But if we're going to use this to branch, we're going to have to take this result as the program counter for the next instruction, I think. Or maybe an offset. I guess we'll take it as an offset because these branches are offset based. So for now, let's do it that way. So we'll say this is an offset now. We should make -1 a constant just so this is more readable. And so we'll say here, if offset returned is 0, then we go on to the next instruction, which is what we've been doing all along. So this goes here. And then if it's a -1, then we're going to return from the method. Otherwise, we're going to jump. So now we need to handle the offset here. We're going to have to pass in the offset when we create our opcode. So this will be a read, short. All right, and then here we're going to need our opcode. I guess making this an int makes our switch statement simpler, probably. And our offset is a short. All right, so now this is going to pop 2 values. Well, it depends on the opcode. Was it A4? I think it was A4. All right, and A4 was compare less than or equal. We probably don't need a comment. This is going to be obvious. All of these are going to pop 2 integers. I think op2 was on top of the stack. So here we'll say, all right, so we'll say success. These are going to fit on one line, aren't they? Less than or equal to op2. We'll add a default case in case we forget something sometime. And then here we're going to say if success, then we return the offset. Otherwise, we're going to return 0 and just go on to the next instruction. All right, let's run the program. Okay, we've got an attribute here that we haven't seen before. It's a stack map table. So let's figure out what that is. So the stack map table is used during the process of verification by type checking. And we're not going to do this, I think. Yeah, so the VM is supposed to do a bunch of checking to make sure that the class file is safe. And there are all these rules about how the class needs to work. But I think we're just going to assume for now that the compiler has taken care of that for us. And we're going to ignore the whole thing. So I think we're just not even going to store this in objects for now. We'll just consume the data, which is actually convenient. The fact that the attributes have their length in them, and then they have the length again in their special format. Seemed annoying, but I think that actually is going to work out for us here. So for a default case, when we see an attribute we don't recognize, we're throwing an exception. Let's add another case here that's going to handle things we don't care about. So in this case, we need to read enough data to get past our attribute, right? This is really the length. We were not using it before. Maybe we should have ignored some of the other attributes that we're already handling, in fact. But right now, we'll just say for this attribute, we're going to eat the bytes and just throw them away. I guess we'll return a dummy attribute for it too. We do need the indices. We might need the indices in the attribute table to line up. Do we care? We might not care. Let's try returning a null here, and we'll keep going until something explodes. So it looks like our top level attribute list isn't actually saving the attributes. And then we also have several places where we're reading it. So if we're going to return null here, we need to handle it in 3 places. This is kind of ugly no matter what we do. I guess rather than do that, we'll create a dummy attribute here. Attribute is an abstract class. That means we need a constructor. So we can do this, and we'll just ignore our stack map table, and now we should get past that. We probably ought to log these too. Okay, so we hit an opcode A4 here. That's because of the silliness with negative opcodes. And now we're hitting A7. Okay, so if we go back to our Java P, there must have been another new, oh yeah, there was another new one to go to. So that's an A7. Let's have a look at that. Okay, so goto is going to read a short offset and then jump to that address every time. All right, so I guess that one goes down here. And we need our offsets. And And this just always jumps, so we always return the offset. All right, so now this should compile. Oh yeah, I need to get the offset in here. Oh, this is op, not opcode. Did I name the other one badly? No, okay. So now if I run it, it might work. It occurs to me that I didn't really check what the offset should be very closely. So let's look at that again. These are an offset. So it's that offset from the address of the opcode of the goto instruction. So if we're in engine, so this is going to be a problem. We have a list of operation objects that we've translated from our bytecodes, and we've lost that information, right? The byte offsets where these opcodes came from. So we're going to have to translate our offsets somehow. There are a couple of ways we could do this. We could sort of rework the way our engine works. I don't really want to do that. Another possibility is to track the offsets in the parser as we process the opcodes. So the other thing we could do is in the translator here, as we process our operations, we can keep track of the offsets here. Yes, let's do that. So we're going to make this a tree map because we need to keep our entries sorted, because at the end we're going to convert this to a list of operations. So we'll say it's a tree map from the offset, which will be an integer, to an operation object. Okay, we've got a tree map. Now, we also need to keep track of where the opcode started here. So let's say this. And then every time we add anything here, we're going to need to use that index. So here we're going to say opcode start. Oh, yeah. Forgot the comma. Okay. Okay, so now we have a map from bytecode offset to operation. We can resolve branches, but right now we can only resolve them if they're backward branches. So where are we using this list? Should we change this to have a map? Maybe we should just change this thing to be a map. I don't think that would be too painful. Let's go ahead and do that. So we'll make this a map from integer to operation. And then translator test will break, which is okay. You only have to fix this in one place because we wrote this text exec method. So that really makes that look like a good design decision. This is a map from integer. When we call execute, we're going to give it our map. So let's update this to take a map. We still have an issue, don't we? I guess there's not a nice way to go through these operations one by one now. We can iterate through them, and then when there's a branch, we could go get the opcode that we want. But there's not a way to start iterating again at a certain key, is there? If if I say opcodes.keyset.iterator, yeah, see there's no, it's not a list, right? So that's a set, so we can't iterate through that the way we want to. So this really isn't going to work this way. All right, so let's back up and try a different approach. All right, so back in Translate, we're going to undo this change. Opcode start, we still want. And then I guess we're going to have to add, why are these all wrong now? Oh, yeah. Yeah, creating this is wrong now. Okay. I think what we need to do is in our operation class, we're going to need to have, it's going to become a class, and it's always going to have its offset in it. So we can store a list or a map of those. I mean, a map gets us started, and it works. A map works well when we branch, but we can't really pick up and start iterating from there. I think we'll just go with a list, store a member here. So this will be an abstract class. This is going to be abstract. We're going to have a public int offset, code offset, maybe code offset. And then we need a constructor here. It takes the code offset and stores it. And that means all of our operation classes don't compile anymore. So we're going to have to add this code offset to all of them. Yeah. Good times. All right, so everywhere this happens is leaving. So this needs to be extends operation. And then we're going to need to fix every constructor. So we get our code offset, and then we're going to say super code offset. All right, so most things are compiling again. Let's have a look at engine. So engine, this is going to go back to being a list like it was before. And our execute is not visible anymore. Okay. Yeah, that's because methods are automatically public in an interface, so I made that default access when I changed it. So, okay, and execute is compiling. Our translator needs to pass that code offset everywhere. This should be called code offset probably, just to be consistent. And then all of our opcodes.adds. Oh, yeah, that's okay. Here we need code offset space. Each of these. Maybe I could do it this way. All right, this is telling us we need to rename some things because these should all be ending with op, right? And I think iadd and dadd are going to go away eventually, so they're going to get combined into handling multiple adds. So I'll go ahead and leave them as opcodes because it's kind of a reminder that I need to do something with them later. This probably should be op. Okay, so translator's happy again. What's going on here? Oh yeah, that became invisible. All right, so some of these things, these are sort of utility methods, so make all of these public. All right, now things are generally compiling again. Okay, so let's go back to engine. We know we need to fix the way this logic works. So we have a list of operation now, but now every operation has its code offset. So when we execute and we get a jump offset back here, we're going to figure out what opcode we need based on that offset. So we'll say our destination is the current opcode, code offset plus the offset. So that's the destination we're looking for. And now we're going to go through our list. So this is going to be pretty inefficient, but I don't think we really care that much, do we? I suppose there are two ways we could do this. Yeah, maybe we don't do this here. Yeah, this can actually be the same as it was. So what we want is we're going to update our our branch commands to return an offset that is the number of operations to jump in one direction or the other. So we can handle this in the translator, and then it'll be more efficient because if we have a loop that's going to execute, a million times, we won't have to recalculate the offset or search for the matching operation every time. Okay, so what we'll do then, but we have to do it after, yuck. We can't jump ahead, right? We haven't seen all the opcodes, so we don't know what the ones that are, farther down in the code look like. So we'd have to actually store something temporary and then resolve the branches later. So let's not do that. For now, we're going to do it the inefficient way. And we'll just put a to-do here. So our destination is that. Now we're going to loop through and find the operation that matches. Okay, so now we go find the operation we're looking for. So if the operation in that location has the one that we're after, we're going to jump there. So we'll set PC to I, and then we want to continue with the next operation. And maybe this should be dest offset. And if we get through the list and we can't find it, something has gone horribly wrong. So let's blow up. that seems okay to me, I think. Now let's update our test. It's broken at the moment. So go back to being a list. And it should compile. Okay. So probably our tests will run still. Let's just do that. Make sure we didn't break something horribly. That was a lot of changes at once. All right. And now let's go ahead and run the code. Okay. Unknown compare opcode -92. That's yeah, it's this obnoxious tendency here. Okay. Okay, so our code ran. We got 0, 1, and 3 in our variables. Let's see what it should have been. So x should be 1. And then if x is not greater than 1, so z is going to be 3. And it looks like maybe the compiler optimized out the other variable or something. I didn't look that hard at it before. So we're putting a constant 1 on the stack and storing it in x, loading a 1, or loading variable 1, adding a constant 1, and then comparing those two things. And then, yeah, there is a constant 2 and a constant 3. But it might have been smart enough to know there were only 2 constants. Maybe the compiler figured that out. I guess we can make sure that nothing like that happens. So let's just do this. And now we know there should be 3 variables. They're getting stored for sure, all 3 of them. So let's go ahead and run it now. So this time we should see that z became 3 and y is not modified. Okay, so we got 103. So that seems right. Now if we change this, I guess we can change the value without needing a new opcode. So 0 would cause it to take the other branch. And now we should see that y is initialized and not z. Interesting, we got a new, what is our new one? Now it's doing a less than or equal. Okay, well, we needed to implement that at some point anyway. Let's go ahead and knock those out. Oh, there are special opcodes for comparing with 0. That's that's the reason. All right, let's make this -1 then. That should go back to being the same opcode we used before. You would hope. Okay, so now it's the icomp LE, so this one should work. Okay, and now this time y gets assigned. So it looks like our branch and our comparison is working correctly. All right, so let's add a test to confirm this. Just make sure we don't break things in the future. So we can do a test go to, and this can be really simple. So we can do an iconst and then we'll do a go to which was A7 and then a short. And we're going to have have to jump ahead some distance. So this is a goTo. And then we'll do another iConst. So here we'll say iConst 2, which would put a 2 on the stack, but we're going to skip that command. And then we want to do an iStore 0. And so the idea here is we are going to put a 1 on the stack, we're going to jump over this command, and then we're going to store our 1 in the local variable instead of the 2 that we would have if we didn't jump over it. So this jump needs to go from here to here. So 1, 2, 3, 4, right? I guess we'll say goTo label. I'll put label here so that we can see what's going on. And then we should have 1 local, and it should have the value 1. And we need to rename this. All right, and it's passing. Now, if we jump 3 ahead, we would hit the const 2, and then this should fail. It still doesn't work to run that. Okay, so now the value was 2, and we expected 1, so it didn't jump over that iConst. So, looks good. So there's our goTo. Now, the other one that we need to test was, I forget what it's called, if comp le or something. Yeah, we didn't write this one down, A4. If I comp le, I guess the comment here belongs in this code, although I suppose it's obvious this is a less than or equal. All right, so A4 is less than or equal, and that's what we're going to test now. So this is, I guess we'll say if int le. So we should write 2 cases here, right? We'll do an iConst 1, an iConst 2, actually iConst 1 again, and they're equal, so this would be a case where it's true. So A4 is our if this is if less than or equal, go to label, and that should be true. So it should not push our constant 2 on the stack. And then we'll store this in variable 0. And then we'll have another case, another test for this. Now we'll push one that is less. So we'll do iConst 0 or iConst 2. I guess here we'll do an iConst 2. 1 is less than or equal to 2. I'm sorry, we need one that's not less. So we should reverse this. It should be 2 compared to 1. So 2 is not less than or equal. So this branch will not happen. And that means we're going to push a 2. Oh, hang on. We need another iConst 1. All right. So the first iConst 1 here is the constant we're going to be storing later. The other 2 iConst 1s are the values we're comparing. The less than or equal should be true, so we should jump over this, and then we'll store. So this if consumes these 2, and then this one gets stored into variable 0. Then we're going to do it again. So our value 1 needs to be pushed. Then we're going to compare 2 and 1, and it's going to be false. So we'll keep going, and now the 2 will get pushed. And then we're going to do an iStore into 1. And then we return. So now we have 2 locals that are going to tell us how the 2 comparisons went. So the first one should have skipped over the const 2 and it should have stored the original 1. The second one should not skip it and it should store a 2. Okay, so this pattern is going to work for all of our if comparisons. So now we can start filling in the rest of these opcodes. All right, so we have these icomp if opcodes. Here we go. We've got our 6 of these, and then we've got 6 more that are, I guess, always comparing with 0. So we probably want to fill in all of these. So let's go ahead and do that. So 9F through A4, huh? These 6. 9F is equal A0 is not equal. A1 is less than. Then we've got greater than or equal, greater than. All right. That takes care of these. And then the rest of these, I just want to check what's going on with those. So I think we're not popping anything. Yeah, we're only popping one value for these. So these are going to be, these have to be a different operation. I guess we should write tests for these. I think we can flesh this out and make it a loop that's going to test them all. I mean, we could copy and paste this a bunch of times and put different values in or something. But let's store 3 variables. We'll do one where the first value is less. We'll do one where the first value is equal. And we'll do one where the first value is greater. So we'll do less, which will be 4 and then 5. So this is a 1 and then a 2. Oh wait, I did that backward. This one is the value we're going to store. So maybe these should be 0 and 1 for true and false. I think I like that better. And so this one should be a 1. This should be a 0 for false. And then this will be the less than. So we're going to put a 1 and a 2. And then we're going to do our operation. And if it's true, we'll skip over the 0. So we'll wind up storing a 1 in our variable. Okay, so that part seems good. And we're going to do this 3 times. So now we're going to use a true value. And in this case, the 2 values will be equal. Let's make them 2s just so we're not using 1s all over the place. This time they're equal. We do our comparison, store a 1 or a 0 into variable 1. All right, and then for the third one, we should go 2, 1. Do the jump, constant 0 is right, but we're going to store this in variable 2. So D, right? And now for our less than or equal, this is less, this is equal. So the first 2 should be true, and the third one should be false. Okay, we forgot to make our local length 3. All right, now we can fill in the rest of these. So we'll say expected locals. And then I can say, what's our first one? Okay, here we have these. So our equal was first, so that's going to be 0, 1, 0. And our opcodes, I guess it's 9F plus. Okay, so we're going to have a loop here. So we're going to say for it's less than expected length. And then for each test, we're going to say opcode uh, 9F plus test 9. And then here for our A4s, this will be opcode. Max locals is 3, test exec is right, and then here our expected result is going to be expected locals sub test 9. All right, so now we're going to do this 6 times. And it goes equal, not equal, so not equal should be the opposite. Less than, so less happens only on the first one. Greater than or equal is the opposite of that. Then we have greater than, which is only the last one. And we have less than or equal. And this should be exercising all of our opcodes. We need another brace here. All right, let's see if this works. Okay, we got that negative thing again. All right, so that's probably in my compare op. No, it's not here. Where is this a problem? If this is a byte, we don't need these casts anymore. And I'm not sure why this would be wrong. Opcodes is an array of bytes. So that can't be wrong. Oh, I know what it is. Okay, in our translator, yeah, we really do have unknown opcodes. All right, so this is, the range here was 9F to A4, I believe it was. So here, we really want to check a range. All right. That's more like it. Now, this is, again, one of those tests where it passed the first time, so we need to make sure these are really being used. So let's tweak a couple and make sure it breaks. All right, so that failed. Now we can try changing another one and just see that it fails. And we can feel pretty good about the test then. And let's make sure everything still passes. Great. All right, so now we can handle these other if opcodes that are comparing to 0. I guess we'll call it if compare 0 up. And we'll have a, no, we don't have any data, right? And then execute's going to do a switch based on this. And we always pop one thing, right? So I guess we'll have a Boolean for success. Oh, we do need an opcode. What was I thinking? It makes our switch nicer. No, it doesn't. I think that actually is going to make it worse. Doesn't really matter. So 99 is equal, so we're going to say success equals val equals 0. And then we just fill in the rest of these. So A is not equal, B is less than or equal, sorry, it's less than strictly. C is greater or equal, D is greater, and E is less than or equal. And we're going to say success set or return 0. 99 to 9E. So back here, we need another case. I guess these go before the other two. Oh, we are going to need a read short, aren't we? So I really should have looked at this opcode. Okay, so yeah, we do need to read the destination. We do need to pass that in. So offset opcode destination, that's fine. We can call this dest offset. All right, and we need our destination offset here. And we actually forgot to store our opcode before. And over here, maybe our offset should be called dest offset, just be less confusing. All right, so now we've got this compare 0 op. And this should be dest offset. See, I screwed up because the name was weird or unhelpful. So the test for this is going to be a little simpler, I think. We're going to have these 6 cases. So it's equal, not equal, less than, greater than or equal. Okay, so the order appears to be the same. Greater and less than or equal. Now our logic here is going to be a little bit different. So we're going to have our 2 values. So we're not going to have 2 values this time. We're only going to have 1. And what matters is how it compares to 0. So we need one that's less than 0. Luckily, we have an iconst -1 that we can use. And then we'll use our opcode. Jump 4 is still correct. Store 0 is still correct. Then we have a 1. We're going to have an iconst 0 here. So it's equal to 0. And then we'll store it. And then we have a 1. And we'll have another 1. And store it in 2. All right, so that looks good. The difference is going to be the range of the opcodes. So these go from 99 to 9E. So we're going to start with 99 here. And then let's see if this works. Okay, so that one passes. Again, let's just break it once, make sure it actually runs. All right. Okay, so that takes care of the branch commands that deal with integers. So here we have a couple that are going to deal with references, I think. A seems to be a reference, so it's probably address. And then we do have a few here that compare long, float, and double. I'm not sure what the G's are here. So maybe we should try to recreate these or take a look at what they are at least. Okay, this is just a compare operation. So this is going to pop two floats, compare them, and push a result. So that's not really a branch instruction. I wanted to knock out the branch instructions here. These look like these are all just compares. We do have some more instructions that control our program flow, but JSR is probably a jump subroutine, so that's a function call. We're not going to worry about that yet. Ret and return both do something. Those are kind of interesting. I'm going to look at what JSR and ret do. But I think that's going to be it for ifs. Okay, so let's just check out JSR and ret and see what those are, but I don't think there's something we want to deal with right now. Okay, yeah, these are something to do with function calls that are maybe deprecated. All right, now we have if statements. I think we can handle just about any if statement that involves integers at this point. There are a few more opcodes we're going to have to handle if we want to include floats or doubles or longs in our if conditions. Thanks for watching. Don't forget to like and subscribe.